Good morning, everybody. So glad to
Morning.
see so many of you here. Um, so, building software has changed a lot over the past decade. Not only did we change the way we did it from a methodology perspective, using agile ways of building our software, you also see that the way we, on the technical side, build our software has changed a lot. In the past, we had our data centers where we could buy a server which would be up 24/7, and that's what we could rely on. But nowadays, we're using this new type of infrastructure which uses, you might say, standard kind of servers that might fail any time of day. So now all of a sudden, we need to build software that is more resilient and can be resilient against those failures and against those painful outages that might happen in, for example, the data centers. So the question might be, but what do you mean by that whole DevOps style thing? How are you going to do a Docker container cluster DevOps style? Well, DevOps style has all to do with the whole notion of DevOps in general. So DevOps is nothing more than the union of people and process to enable continuous delivery of value to your end users. And that means that we try to work in what we call value streams that deliver value to the end user as fast as possible. But while we do so, how would that work when you build a mission critical system? I mean, it's great to do these kinds of things for an app that might be only available at office hours, but how do you make this actually a reality when you build a mission critical system? A mission critical system that you build, but you also run it instead of run away, because that's what we tend to do as developers. And now we need to own the code, we need to actually operate it, and that's what we want to share with you today. So where would you rather spend your weekend? Would you like to spend your weekend in the office? Or would you rather spend your weekend here with your dog in the hammock, if you have a dog, by the way, but at least chilling out and not worrying about your mission critical system while you are on call. You have pager duty. And that's what we want to share with you today. So,
To do that, I want to show you the system that we actually built. We're not just talking about theory here, we've actually got a system running in production as we speak. Alright, so what did we do? So, there's a big hole below the Netherlands, and that big hole that used to be filled with natural gas. And one day the hole became empty, and some clever energy company decided to purchase that hole. And they now use it as a sort of parking garage or a bank for natural gas. So what they do is they rent out space to other customers, and they can put their natural gas in it in the summer when it's cheap, so they can sell it in the winter when it's more expensive. And the company makes money by billing the customers for those transactions. So we actually built this system. And there's a couple of things that are important for this system. One thing is that it's absolutely time critical. So if a customer says some gas needs to be pumped out, it needs to happen immediately and not in a few days. So this is the mission critical part of the system. And also, there are no buffers in the gas network. So whatever you pump in needs to be consumed on the other end of the pipeline. And just to give you an imagination about how big this plant actually is, it can provide the whole country of the Netherlands with gas for a full day by just pumping gas out of this bubble. So it's really a huge deal. So we built this system, and I want to tell you about how we made it resilient. Well, how can we show it better than just to give you a quick demo? Alright, so this is the system. Of course, it's not the actual system, but it's a reproduction. And well, it first requires me to log in. And once I did that, I will see that I am able, as a customer, to now inject a little bit of gas into the system. Oh, that's interesting. Something is going wrong. Well, this is obviously all staged, so don't worry about it. So what you can see is whenever I hit the inject button, we get some errors, and apparently the system is broken. You can see that the gas in store for the customer is being updated, but the entire gas storage fill level, it's somewhat lagging, and well, there's an issue there.
Yep. So the way this system is built is as follows. So we have these different layers now there.
Yeah, so we have a single page web application. It's built in React, and well, it's able to run inside your browser, and whenever you click a button, it doesn't do a post back. Now it just generates a bit of JSON, and it will be sent to a .NET Core web API. This web API takes the transaction, for example a customer who wants to inject some gas, and it stores it in a buffer, and then there's background processing that forwards the call to the plant. So well, there may be an issue there.
Yep. So this is the app that we now use as demonstration purpose, because it didn't really make sense to actually now steer the plant and then make gas pump in and out there, right? So I hope you bear with us that we used a little demo app now to simulate what we actually did in the production system that we built. So it's important that if you look at how we built this system, there were many things that come into play when you need to run this in a DevOps style. So you need to think a lot about how you build this system in a resilient way, how you cope with failures of backend systems, but also how do I operate such a thing? I mean, if you build it and you only check in your code, how does it get to production, and how do we make sure that the moment we do have an issue, we still can move code forward into the production environment and mitigate problems that we might have? So many things that we need to think about, things like Jira application, computer clusters, and we will show you later in the demos what's behind the scenes and how this actually works. So when we build systems, I think that most of you probably do not know how the system is actually being used. One of the things that we face is that we build the software, we put it in production, and then, well, we know that it kind of works because we didn't get any calls from our service agents, for example, that found that there was an outage of our software. So we see that we 9 out of 10 times fly in the blind because we do not actually know what's going on with our software. And the thing is that we need to constantly monitor the system stability that we have. I mean, what happens when we did a new deployment? How did we actually move that to production, ensuring that no incidents will happen the moment we push it to production? And with this, we need to have a look at not only the fact that there is an absence of errors, because that's some of the things that we often do, right? So we then move stuff to production, and then we say, oh, there are no errors, we do not see anything in the error log, so things must be okay. Well, what we learned over time is that it's critically important to not only look for the absence of errors, because when we deployed something to production, we actually could have changed the system's behavior in such a way that it would cause problems in a couple of hours or perhaps in a couple of days because we made some mistakes. So it's critically important that you monitor your memory usage, your CPU usage, the cache that's being used, for example, in your system. Some of the things that can show you that the system is going the wrong direction is, for example, if you see that there are all of a sudden a lot of cache misses instead of hits, that you see that constantly objects are being refreshed in your cache, which normally should not be the case, because your cache, well, it's a cache, right? It needs to cache stuff and not constantly change in the meanwhile. The other thing that you need to watch out for is a lot of I/O that starts to happen all of a sudden. Especially when you're using, for example, cloud providers. They tend to charge you for I/O. So all of a sudden your system might still be up and running, but all of a sudden your bill that you get from AWS or from Azure might all of a sudden be doubled because of the I/O that you incur. So those are the things that you need to keep in mind. And to give you a little example here, this is what we use a lot is application insights to see what is being used in our applications. And you see here on the left hand side a system that is running perfectly okay. And on the right hand side it's the same system but after a new deployment. But the thing is, if you look at the red side of things, that's where the errors are, and you see on both sides of the equation that this system looks healthy from an error rate perspective. What's actually going on here? Well, in the left-hand side, you see that this thing was going on with CPU levels somewhere around, 40%. but now I deployed a new piece of software, and all of a sudden I see the CPU going to 0. I see it spike all of a sudden, and that is a thing that you can see, oh, this system is not healthy. It's jumping up and down, and it doesn't know where it's going. You need to have something that is stable and plunking away. The other thing what you see happening is that all of a sudden the request to a third-party endpoint, for example a database, now has all kinds of strange things going on. You see that the call rate is going down. You see that the time that it takes to do a call is going up, and it's showing a strange distribution, which is also indicating that this system is not healthy. And last but not least, the response times of this system all of a sudden become very long. So all of a sudden now we are in the seconds instead of the milliseconds if it comes to response times. So clearly something happened here, but no errors happened while deploying, and there were no errors while it was in production. And those are the things that you really need to look out for. And Loek has some good insights in that, and building monitoring and alerting in this.
Yeah, well, alerting is nice, but alerting on its own is not enough. So you need to act on the alerts that you get. So first of all, you monitor your system, it generates metrics, and then you need to think of what metrics are regular metrics and what metrics are not. And once you encounter an irregular metric, you need to have a system that will, for example, start paging the engineer on duty. We chose to use a platform called VictorOps for that. So whenever we encounter an issue in our system, one of the monitors will alert VictorOps, and VictorOps will call the engineer on duty. Well, if you think about your system, memory is nice, CPU is nice, but well, billing is another example, but also security. So if you are suddenly being DDoSed, you also want to know about that. So monitoring and alerting on a much greater level than you would expect. So, yeah, you already know that the system is broken, but now let's have a look and see if we can find out what is wrong with it. And for this, I will show you the real version of App Insights, not just the pictures, and just give it a little refresh here. This is obviously been prepared, so I'm expecting to see a little bit of an error rate here, and well, it's already there. Just do a little refresh just to be sure. It's always a little bit exciting. Well, what I want to show you is the application map of Application Insights, and this can help you very quickly find out what the problem is in the system. So this is my front end. You can see that it generates metrics, and it's generally fine. And then it's hitting one of the instances of the backend. And as I already mentioned, the backend does background processing and forwards calls to the plant system. And most of the calls to the plant system seem to be failing. Well, let's zoom in and find out what's wrong. Well, you can immediately see here that we have encountered 700 error 500s. Error code 500, and well, that's an issue, of course. If you zoom in on one of those issues, just pick any because they are all the same in this case, you can very quickly see what's wrong by just having a look at the timeline here. So you can see that the posts to the plant are actually failing. A lot of the calls are failing, and if you click on one of those exclamation marks here, you can see that there's an error I'm generating here. Maybe you cannot see. Let's zoom in for just a second.
You program your bugs in there. That's
yeah,
okay.
Like I said, it's staged. There's an exception that's getting thrown from the plant process, and whenever we try to call it, it generates errors.
So what's very important as a takeaway from what Loek just showed you is that application insights is only a right click away to get it into your application. I'm not sure if you done any development with Microsoft technologies, but normally it's nothing more than just adding a package to your solution, adding 1 or 2 initialization calls, and you get all this for free. And you get for free all the information if it comes to the calls that are that come into the system, the flow through your system. So even if you're hitting multiple endpoints like we did, so we have a front end, a middle tier, and the middle tier going to a back end service, and that even going to the database, you can track that completely, so you can exactly see what is going on in your applications. Application Insights is a real helpful tool for us, at least, to get these insights on how our system is doing and where failures might be coming from, and that helps us figuring out what is going on in the system when stuff is breaking at the end user level. So what you've seen is that although that you might have telemetry, your system still shows a user interface, but there's something going on and something is going wrong there. And what we like to discuss here is what are the things that we need to do to make things more resilient. Because, like I said, we changed the way that we now have compute these days, so our compute might fail. We do not always get the answer back that we might expect. So we need to build in resilience patterns in order to build these mission critical systems that we can actually rely on without us having to spend our weekends in our offices. We really want to be at home and just be very happy about the fact that our system is running. So what are the things that you need to look at? Well, an important thing of that is, for example, the single point of failure. Now, I'm not sure if you have often done that, but if you look at your application architecture, it's very important to look at what are my single points of failure in this system. And if this system fails on that particular point, what is a way to get rid of that problem? Is that a failover that we need to do? Do we need to go to, for example, something that we duplicated? Do we need to find different ways or store the data locally and then finally get it back? So we have a look at what we can do. So from a perspective of a single point of failure, what we can do is, of course, very simply create a redundant system. But that's easier to said than done. I mean, if you need to fill over, let's say, to a secondary SQL server that you might want to have in another region, okay, but what is the amount of data that I might lose? I mean, of course, within for example, Azure regions, you have one SQL server and another SQL server, but still there might be latencies between those different instances. And if you switch from one instance to the other, you might lose a little bit of data. And is that acceptable, yes or no? And how can you reconciliate from that when you do so? The other thing that you need to look at is degraded performance. So what happens the moment something goes wrong in your system? Is then the immediate response, okay, I do not know, and I give a big error message to my end user, good luck with that, and call tech support? Or can you still provide some form of service even though that not all the systems are up and running? And this is some of the things that are often overlooked because if you look at mission critical systems, not every single piece is mission critical. What we see the gas thing is that the calculations need to take place, but you can skip a beat, for example, and that is not that important, but yeah, you really want to send a message to the pump to pump out the gas, so that's more important. So those are the things that really are important to note. And well, the spike in the tire here, I have run flat tires on my car. That means I can have multiple spikes in there, still drive, not as crazy as I normally do, but still I can continue and find the next gas station to get rid of the tire puncture. And those are the things that you need to look at building these systems. Now, one of the other things that's very important that has changed over time is that we nowadays have new technologies that we can use to build resilient systems. And for this we can leverage container technology. And container technology helps us from a perspective that we can build code and move it very easily from, let's say, dev to test to production without making any changes. But the other thing is that we can run it in what we call a cluster orchestrator. And I now show you the logo of Kubernetes as the cluster orchestrator, but there are many more cluster orchestrators that you could use depending on what you really want. Kubernetes is one of the most popular clusters nowadays. It more or less won what we say the container cluster war. But what you see is that, for example, Docker Swarm is still very, very popular. And if I would say that systems that run in production, probably Docker Swarm is much more in favor than Kubernetes at the moment. Kubernetes is what we all build our new stuff on, but Docker Swarm is still there in production, being used a lot. The other thing that's sometimes used is Service Fabric. And Service Fabric is a cluster orchestrator that has a very special niche, you might say. If you want to build systems like we did, which are stateless, then we can run very easily on Kubernetes and Docker Swarm. But if we need stateful services, meaning that you keep state within your container, so you cannot just swap it out and replace it by a new one without any impact on your system, then Service Fabric provides a very nice programming model for that. So Service Fabric is there in a niche, and you can use that on-premise, you can use it in the cloud. There are different options that you can use there. But for now, we see that Kubernetes is one of the things that we use mostly, because often you build a stateless system. Last but not least, what is very important is we need to test and automate everything. Now you might say, okay, Marcel, that's all nice and dandy, but why is this so important? Well, the important part is that if you look from a perspective of mission critical, and I need to, for example, move to another region or another data center, what if I need to re-click all the steps that I have done in the past? I really need to have automated pipelines to not only provision my software to the servers, but also my infrastructure. So what you really need to do is automate your infrastructure provisioning and automate your software deployment on top of that. And both are very important. So automate everything. That's the way you will get your weekends back, and that's very important. So, Loek, can you show us some of the resiliency that's been built into the app?
Yeah. So let's look at the actual source code of the app, and then I can show you what I mean. For example, you could see in the tracking in the app insights, in the error. Sorry. Yeah. What you can see is it's not just one post that's failing. It's apparently well, at least 4 posts here, and it's a period of about 10 seconds. And that's not a coincidence, because when I design my system, the backend system that calls the plant, I already expected the plant to sometimes fail. So for this, I use Poly, and Poly can easily be combined nowadays with the HTTP client factory. And by using a few clever policies here, the overall timeout, the timeout per try, and configuring the HTTP client over here. Trying to select, right? I can build an HTTP client, which I can use using dependency injection in my controller, that's in my processor that calls the plant. If I look at the code over there, you will see it's an hosted service, and a hosted service is something that shares the lifecycle of the entire application process. So whenever my web server starts, this hosted service starts as a singleton. And whenever my process dies, this thing dies as well. It comes with 2 methods out of the box: start async and stop async. These are calls automatically by the runtime whenever it's time to start running this service. And what I do in this service is just a while through loop. Until stop is called, I'm just looping. And every 2 seconds, I'm trying to process pending transactions. So customers send in their request to withdraw or inject, and every once in a while I take a look at what they are asking and post that to the plant. The HTTP client I was talking about is this plant client, and I'm using a library called refit to generate this the concrete type of this interface. So whenever I want to call my plant API, I just define the interface, and in startup I register a refit instance for that plant client. This is all I need to do to generate a strong typed client based on the interface. And inside the flow processor, I can start calling that API, and whenever it succeeds, I I update my pending transactions. I set them to processed, so they won't be processed in the next loop, and I continue the cycle again. After I've successfully processed the amount of transactions, I need to update the React frontend, and I'm using SignalR for that. So while I'm doing background processing, I still get in touch with the frontend. And that was why the error message just popped up while I was typing earlier. Right.
Okay. Yeah, so the key takeaways I would say for this is that when we are calling other systems, we are very used to the fact, oh, we're just doing a connection to a database, or we're just doing an HTTP request. But instead of that, inject into that call chain always something that does retry for you, that might do a circuit breaker for you, that are ways of making this code more resilient to all these outages that you might have. And you see how easy it is. Nothing more than injecting poly, which is nothing more than an additional framework step that you can do to make this happen. Now you can also use other technologies than what we did. We did it here in code. There are other technologies like Istio, for example, which you can just inject into your Kubernetes cluster, which will then do the HTTP retries and all those kind of things as part of the service mesh there. So there are different options that you have. The moment we started building all of this, that was not available yet, but you see that this ecosystem is evolving all the time, and that means that your custom client code can be very simple, but still be very resilient. But just keep in mind, do not just do an HTTP call, because HTTP is known for not being reliable. You might get something back that you don't expect. So what Loek did with poly, for example, was a retry pattern already, where you saw that it's retrying the moment it gets an error. That's one of the patterns that's very common to use. Another one that's very common to use, it does, of course, the retry. What is important, by the way, is that when you start retrying, make sure that you're not trying to do a denial of service attack on your own system. And what I mean by that is that if you are constantly failing and then you're backing off, do not start to call all of a sudden with all your services to that backend service again, which is just coming up again, and oh, I'm finally here, and then gets hammered again with all kinds of requests. So you need to nicely, gradually do those calls into that system. The other thing that you might use is the circuit breaker pattern. The moment you get a call out and you get an error back, you might do the retry, but you can keep retrying. If the system is not there, you're just wasting your time. You just know it won't be there for a while. So then you can pop the circuit breaker and go into a different pattern, for example. So you might say, instead of pushing stuff into a SQL server, now I'm going to store it in a local queue. And the moment the database comes up again, that's the moment I will start reprocessing all those messages, which then, of course, requires an architecture that supports the fact that you might have missed some events and you can still replay them on a database, for example, using CQRS. The other important pattern, and I think that saved you guys a couple of times if it comes to the gas pump station, is that the outbox pattern. And the outbox pattern is we will store our data also in a secondary part, and the moment that a system becomes available, I start pushing those messages again. So the moment I see that I cannot deliver my messages, I just push it into local storage, and then finally start pushing it. And you saw the backend loop that was running, the while loop that is looking for transactions that still need to be completed. Well, that is a way to see, okay, I have some backlog of transactions that I still need to take care of, and that's what I'm going to push out later. So you're buffering the outgoing data and you upload in the background instead of doing it right away, which makes it much more resilient than just doing the call that you normally do with a request reply. So can you show a little bit of the patterns there?
Well, let's have a quick look at the code again. So now that we know the names of the design patterns, you can actually see that by configuring poly policy here with the retry, wait and retry, I'm doing 10 retries, and for each retry attempt I'm increasing the amount of wait time in between the retries. So this is the retry pattern by using the poly library. You could do the same thing with the circuit breaker. Poly also offers a circuit breaker. And by combining the two, you can prevent everybody having to find out themselves that your database is down. So one connection fails, you break the circuit breaker and the other guys don't have to retry. And what you saw here indeed was by just caching some stuff in a local list before sending it out, I can actually just say to the user, I have received your transaction successfully. I will send 202 accepted back to the user, and then in my own time in the background I'm starting to process that message, and eventually it will probably get there to the plant, and then because of the use of SignalR, I can notify the client that his transaction was in fact processed.
Yeah, and it's a different way than you normally do when you just do an update in the database and go back to the client and say, oh, I'm fine. No, you're just doing the stuff in the background and then signal back that you actually have done stuff. And that's yeah, much more resilient in that way. So, what could possibly go wrong, right? If you build this system, you run it on Azure, you think, well, they have big data centers, they can do failover. They did their analysis of their data center and make sure that we don't have outages, right? So what could possibly go wrong in an Azure data center? Well, if you look at the outages that we had to deal with the past few weeks, it was more or less insane, right? It was really a lot of stuff that went on. If you would look at, for example, the status page on Azure, you can see there that there is a lot of stuff that just went wrong. We just have a redundant failover system on the mics, I see, so that's also good. We're getting the battery switched, so that means that I will now show you here that one of the things that we saw here are 2 outages, for example, and one of them was a very important one that had to do with SQL Server. So SQL Server in Western Europe was not available. What do you do when you have something that relies on SQL Server? Well, here we had the outbox pattern that we could use, and we could just store stuff on the side and then actually reconciliate the moment things went wrong.
Yeah, so what we did in this case, we just failed over. So we have an identical copy of the system running in North Europe. The original copy runs in West Europe. And what we did, we flipped the switch, and voila, the DNS record was changed, and the SQL failover group now pointed to North Europe, and the issue was resolved for us. So the customers, well, they did see a small hiccup, but it was, well, very minor. I can show you that is true by showing the status page. All of our systems have 100% uptime, except for that well, disaster day in the 7th of May. We had about an hour and a half of official outage. In reality, it was about 5 minutes before we flipped the switch.
But this has to do with the fact that we didn't close the ticket fast enough.
Yes, yeah. It was a human error.
Human error that makes it longer than actually necessary. The actual outage is just very shortly. You can show the App Insights graph as well there, right?
Yep.
Yeah.
This is the graph of the moment in time that the error happened. And you can see that all of our systems are actually running fine. Oh, you cannot see that. We lost the number while walking here. That's interesting. Yeah, now it lost the date. Well, doesn't matter. It would show that all the systems had 100% availability, except for that one single subsystem that was unavailable for just a few minutes.
And we're running this all on a Kubernetes cluster, by the way. So everything is in containers, it runs in Kubernetes, and that's the way we do our stuff. So that's where also perhaps, I'm not sure if you have the dashboard up here, we can show that the stuff is running there. But other than that, yeah, that is more or less, well, you run a cluster in production. That means that we now have all the advantages of a Kubernetes cluster, making sure that the moment we need to, for example, do an upgrade of our software, we can do a zero-down upgrade on that. Or we can have failovers of nodes that might fail in the Azure data center, and all of a sudden our pods get rescheduled on other nodes. And this is the other picture you had.
Yeah, now it does have the percentages.
Yeah,
I took a screenshot earlier.
Ah, good.
Right, back to the slides.
Yeah. So the outages of the past weeks, and more or less this is what we wanted to show you. So how can we keep sleeping while our system is running? This is how we prefer to spend our weekends. And we were able to do so by building all in these resilient patterns and making sure that you do the failovers, and of course running on containers and on a container cluster. But that is one of the things that a container cluster these days is just infrastructure for us, nothing more than just running on hardware. So wrapping it up, DevOps means you build it, you run it. That means that you need to build something so that you actually can support it in production, which is quite important. We've seen that there are a couple of things that we need to do if it comes to the approaches there. So we need to build in the redundancy of our system, make sure that you can do the failover to another data center and that you are prepared for that. It's just nothing more than flipping a switch. That you are able to work with degraded performance and the degraded state of performance, and have some alternative routes there. Use clusters like which we are using is Azure Kubernetes services, which runs on the Microsoft Azure platform. And then automate everything. So not only automate your deployments to production if it comes to the software, but also automate all your infrastructure deployments to the different regions using, for example, ARM templates. And you guys are also using Pastor tests to actually validate it, right?
Yeah, that's correct.
Yeah. And then finally, the patterns that we use a lot, and we place them in software, is circuit breaker patterns, the retry pattern, very important to do an exponential back off on that, and do not start to fire up immediately the moment the system is online again. Use the outbox pattern to do the processing after the fact if something failed. And with that, we want to thank you so much for your time.